Hello everybody and welcome to this video on sections 2.7 and 8.1. You are watching this video because Dalton and I are partying it up at a math conference while all of you stay back at Jewel and do sad things that aren't math. So in lieu of having class, you will watch this video about these two brief sections on the numerical approximation technique known as Euler's method. So before getting into it, I just wanted to show you a brief clip from the movie Hidden Figures. So to give you some context here, Hidden Figures is about the role of three African-American women in helping us get a rocket to the moon back in the 1960s. So this brief clip I want to show you is only 2 minutes long, and Euler's method comes up in that context of getting a rocket to the moon. So go ahead and copy and paste this link into a web browser. Pause this video, of course, watch this 2-minute clip, and then come back to me. Okay, so I assume that you have now come back to this video after watching that video. So a couple of comments. First of all, it's nice to hear swelling inspirational music when somebody opens a math textbook in a movie. That doesn't happen very often. Also, notice from their conversation what's going on. They're trying to solve an equation, and from the math that's on the board, on that chalkboard, it's not clear that they're solving a differential equation, I guess. Maybe if you pause it and zoom in, you can see the differential equations. But that's what they need to do. They need to solve a differential equation. And they say, well, we can't do it theoretically. We'll have to do it numerically. So we're going to unpack what that means through these sections. But basically what they're saying is, they don't have any theoretical analytical tools to solve a differential equation they're interested in. And so what do you do, right? What do you do when you can't just go to like the theory of chapter 3, where we actually built a theory to solve certain differential equations? What do you do when there is no theory to solve your differential equation? Euler's method lets you at least get an approximation of the solution. So here's sort of a more formal introduction. Suppose I come to you and I say, I want you to solve this differential equation for me. Or I guess it's actually an initial value problem, right? Because I tell you when x is 0, y is 1. Solve this initial value problem. What is your reaction to this command from me? I don't know, but your reaction should be this. I don't know how to solve this, right? There's like an absolute value in there. X's and y's are kind of mixed together. This equation is not separable. It's not first order linear. There's no box you can put this equation in that we have dealt with so far. So you should just sort of, you should shrug at me and say, I don't know, that's a bad question. But suppose I come to you and I say, well, I really, really need this solved, right? It's really important to me in my life. This is modeling getting a rocket to a moon or whatever, right? What can you do? Well, the answer is you actually can't solve this analytically using theoretical tools, but if you just want to know what a graph looks like, you just want an approximate graph of the solution, you can build one and you use Euler's method. So that's the idea of this section. Here's a DE we don't know how to solve, but we want to get a solution graph. How can we get an approximate solution graph? Okay, so that's what Euler's method does for you. It's a way to draw a graph that's an approximate solution of an initial value problem that you can't solve. How does the method work? Well, if all you want to do is draw a graph and you don't care about an equation, notice, since you're dealing with an initial value problem, you get a point on the graph of the solution for free. So back here, I've already told you that 0, 1 is a point on the graph. So if you want to build a graph, you get 1 point already. So you know that your solution will go through the point 0, 1. So the initial value part of the IVP gives you a point on the graph, a single point. Since you have a differential equation, though, not just that initial value, you're given slope data. And what is slope data, right? Well, it lets you know approximately how much a solution rises or falls from a given point on the solution. In other words, this initial value problem here, right? If x is starting at 0, then y will start at 1. So 0, 1 is a point on the graph. From 0, 1, where does the graph go? Well, that's hard to say, right? But at the very least, you're told what the rate of change of y is. So you're told about tangent slope data, and tangent slope data tells you how much a graph is rising or falling at a given point, right? Calculus 1 is all about that, right? So you took basically an entire course on that concept. So anyway, Euler's method just says, well, if you know a point already and you're given tangent slope data, then given any point you're at currently, you can estimate how much you rise or fall as you're drawing a graph. So let's just actually just trace that out with this example. We know 0, 1 is a point on the graph. How fast is the graph rising or falling, I guess, right, at that point? Well, to figure that out, you're given a formula for slopes of tangent lines, right? Y prime is all this stuff. If you know an x value and you know a y value, you can tell me the slope at that point, the tangent line slope. So if x is 0 and y is 1, then this term disappears because x is 0. And then if y is 1, you got 2 minus 1 is 1. Absolute value of 1 is 1. And then plus another 1 is 2. What does that mean? That means that the graph is rising from the point 0, 1, and it's rising at a rate of 2. In particular, what that means is that if you want to take a single x step to the right, like going from x equals 0, where I currently am, to x equals 1, the graph itself will rise approximately 2 y steps. That's what this number 2 is saying. So if I started at the point 0, 1, then when I take one step to the right, so that now I'm at x value 1, I'm going to take 2 steps up in the y direction, approximately, right? There's no guarantee it's exactly 2, because tangent lines don't exactly give you a curve, right? So tangent line slopes won't tell you exactly what happens in the future. But anyway, it's an approximation. So if you're at 0, 1, and 1 x step to the right means 2 y steps up, that will land you at this point, 1, 3. So given that 0, 1 is a point on the graph, and given that the graph rises approximately 2 from that point, I can now build a new point on my solution graph. Okay, so that's how Euler's method works. Once I have this point 1, 3, I can just repeat this process, right? Now I have a point 1, 3 on my graph, and I can figure out how much I rise or fall from that point to build a new point, etc. I can just keep going on and on and on. So let's just do one more step. We now have one point that's for sure on the solution, another point that's probably close to something on the solution, an approximate point on the solution. How do we get another point? Well, just ask the same question as we asked before, but replace 0, 1 with 1, 3. How much does the graph rise or fall from 1, 3? Well, again, you are told tangent slope data. So when x is 1 and y is 3, I can just plug those values in. X is 1, right? So 1 squared. Y is 3, so 3 halves. Y is 3, and then plus 1 is always there. And if you add all this up, you get 3.5. So what does that mean? If you take another x step to the right from 1, 3, you're going to take 3.5 y steps up. So taking one x step to the right and 3.5 y steps up from this point, right? That's where we currently are. We will land at that point. So if you want to see this geometrically, let me just show you a picture. So here's a graph, which, oh, I can't actually zoom in, I guess. Well, anyway, so here's a graph that starts at the point 0, 1, that's right there. And then I go to the point 1, 3, and I travel that along a tangent line. This line here is actually the tangent line to the solution. And you know it's the tangent line because it goes through 0, 1, which is a point on the curve, on the solution curve, and it has slope 2, and you got that 2 from the derivative. So basically, I'm just going to travel along this tangent line for one step, one x step, and now I'm at the point 1, 3. And now I know I'm supposed to go from 1, 3 to whatever I said it was, 2, 6.5. So I draw a new tangent line, one that is steeper this time, right? Because my slope was higher. I used to have slope 2, now I have slope 3.5. So anyway, the curve is increasing in steepness here. So I have now an approximation of my solution curve on the interval 0, 2. And then I could keep going, right? I could keep going for as many x steps as I feel like. I could just keep piecing together these linear pieces, and I'll get an approximation of my solution curve. So what you're doing with Euler's method is start with a point you know is on the graph. Then you're going to stitch together an approximate solution graph using the slope data. The graph itself will be piecewise linear, as we just saw. The linear pieces themselves are pieces of tangent lines from the given point that you're currently looking at. Okay, so what I want you to do now is try same differential equation, but with a different start point, 0, 0. And tell me 4 approximate points on the graph of a solution. So you should pause this, try this on your own, and then come back. Okay, assuming you are back now, let me just show you the points. Well, notice the origin was given to you, right? You're told 0, 0 is on the graph. So that's not even approximate, right? So now we need 3 more points. And it turns out these are the 3 you should have gotten, unless I made an error. Let's just check the 1, 3 part, right? If x is 0 and y is 0, right, what does that mean? That means that this term is 0 right here. And then if y is 0, you get a 2 right here. And then plus 1 is 3. So what that means is if you're at the origin and you take 1 x step to the right, you're going to rise by approximately 3. And you will land yourself at 1, 3. From 1, 3, we already know you get a 2, 6.5. And then if you plug x equals 2 and y equals 6.5 in here, you'll get something like 18.5 or something as a rise value. So moving from 2 to 3 in the x gives you a rise from 6.5 to 25 in the y. So there you go. That's how Euler's method works. So a few comments about it. In practice, like if you were actually doing this to send a rocket to the moon, what I just did is like criminally negligent or something. In general, you never take x steps of size 1 because that's way too big. So basically back here, 1, 3 is probably actually really far from the real point that's on the graph. The real point might be like 1, 2.5 or something. Who knows? And you know, the more error you accrue in your first move, that error just compounds as you keep moving to new points. So you want to make sure that you minimize the amount of error you're accruing at each step. And taking such a large x step of size 1 and then 1 and 1, that's bad in practice. You would never actually take such a large x step. So what you would do instead is take an x step of, say, size 0.01 or 0.1 maybe, you know, something very small. And then geometrically what that would correspond to is, what I did here was I drew a tangent line and I followed it for a while, right? I followed it for an entire x step of size 1. If instead your x step was size 0.1, you just wouldn't follow it so far. You would only follow it just a tiny little bit to a point like right here, and you get a new tangent line and follow that for a tiny little bit, a new tangent line, tiny little bit. Whereas here I just only have 2 tangent lines and I follow them for a while. So anyway, in practice, you would take tiny little x steps, so you wouldn't follow tangent lines for so long. You would only follow tangent lines for a tiny little bit. And in fact, when we do this on the computer ourselves, notice this picture, right? It's piecewise linear. You can see the linear pieces. The computer will use x steps so small that the resulting curve will look smooth to the naked eye. Okay, because this, right, this clearly is jagged to us because the x step is so big. But imagine using a tiny little x step, like 0.01 or 0.001 or something. You're going to get tiny, tiny little linear segments. But they are so tiny that when they are stitched together, it will look smooth to you. Okay, so all that to say, right, we ourselves are not going to build an Euler's method calculator. We will use one of our own after this section. So in this section, you should do what I just did for the homework. But anyway, a computer uses much smaller x steps to give much better graphs, much more accurate graphs. We use this technique to solve a single differential equation. You can use the same technique to solve a system if you would like. So here is a system, right? x1 and x2 depend on time, and the rate of change of x1 is given by x1 times x2 plus t. The rate of change of x2 is given by x1 squared plus 2. So now, if you want to solve this system, now you're going to have to draw me 2 separate graphs, a graph for x1 and a graph for x2. Right, so in this scenario, maybe x1 represents a population of foxes, x2 represents a population of rabbits, right? Each of those populations has its own graph. So to solve this system, you want both those graphs. So think about drawing a graph for x1. Well, as before, I've given you a point on the graph, 0, 1, right? And then if you want to know how much you rise or fall from 0, 1, you go to the rate of change data. And right now, right, time is 0, so that t becomes 0. Right now, x1 is 1, right? When time is 0, x1 is 1. Also right now, when time is 0, x2 is 0. So you can plug all three of those values in here, and you get 0. So at least at first, the graph of x1 will not rise. So it's going to stay steady for a little bit. x2, though, on the other hand, right, we know x2's graph starts at the origin. If you want to know how much it rises from the origin, well, when time is 0, x1 is 1. So you get a 1 squared there, plus 2, so you get 3. So initially, the graph of x2 will rise at a rate of 3. And then you just iterate that process, right? We got a couple new points on the graphs of x1 and x2, and then we just keep building off of those points. So at the very beginning of the slides, it says, this is a video about sections 2.7 and 8.1. Your only homework comes from section 2.7, and it is doing this kind of thing, a single differential equation. Section 8.1 deals with systems like this, so I didn't assign any homework over it. I just want you to acknowledge to me that you can use the same kind of technique for systems if you would like to. If you can do it for a single DE, you can do it for a system of DEs. It's the same process. You are just simultaneously building 2 or more graphs at the same time. Finally, a last comment. You need the differential equation itself to look like first order derivative, right? Just a y prime or an x1 prime, whatever the variable is, right? Only a first derivative equals non-derivative stuff, as this equation was, right? Derivative equals non-derivative stuff. If your differential equation looks like anything else, you can't really use this technique because we were directly using slope data, right? So if this were a y double prime, now you are not given directly slope data, right? You are given acceleration data or something, and you can't just directly estimate a rise or fall of the graph of y from that. So anyway, in the homework, you will only see equations like this. These are the equations Euler's method can handle. Of course, in practice, if you need to numerically solve a different kind of DE, there are other techniques out there. But Euler's method, at least as we're presented with it, can only deal with equations like this. Okay, so finally, a last question you might have is, Euler's method is in section 2.7, which is back in chapter 2, right? And we did chapter 2 a long time ago, and since then we've done chapters 3, 4, 6, 7, right? So why are we talking about this now? And the answer is, when we get back on Monday, we're going to start studying models of disease spread. These models consist of systems of differential equations that can't be solved using any tools that we have. In particular, cannot be solved using the tools from chapter 7. So, we will not be using any sort of analytical theoretical technique to solve those DEs. Instead, we will hand those systems over to a computer to get approximate solution graphs. So, all of that to say, why are we discussing this now? Because I wanted you to have some idea of what this computer is doing when it hands you these graphs, okay? So we're going to hand the computer, I guess, what you might consider fairly complicated systems of DEs. But what the computer is actually doing is not that complicated under the hood, right? It's just basically using Calc 1 and stitching together tangent lines to give you curves. So that's what the computer will do next Monday, Wednesday, etc. And I just wanted you to know that's what it was doing. So the algorithmic technique for how the computer gives you these images that we will get is not terribly complicated. Okay, but in terms of homework, this is the homework. You're just going to do this a couple of times. Okay, so I'll see you on Monday. Be sure to email me if you need anything.